All right. In the last video, we learned how to write equilibrium expressions. But knowing what the expression is just step one, right? The real challenge is going to be finding the actual concentrations at equilibrium. And for that, chemists use a very powerful tool called an ice table. An ice table. And here, ice is not referring to the solid state of water, but rather ice is an acronym standing for initial change and equilibrium. So here we get ICE or ice. So an ice table is going to be looking at the initial concentrations, their changes, and the concentrations at equilibrium. So it's just a neat way that we can organize these things together and makes it easy to solve problems where we need to find equilibrium concentrations. So let's look directly at one of these problems, without further ado. All right, so here we're given this chemical reaction, and we're told that N2O4 in its gaseous state is converted to 2 moles of NO2 in its gaseous state. And so we're given the value for the equilibrium constant here, and we're told that's 0.005, and we're given the initial concentration of our N2O4 and the initial concentration of our NO2. And now from this, we need to be able to figure out what the equilibrium concentrations for these compounds will be. So the first step for a problem like this is going to be to write the equilibrium expression. That's something that we should be very familiar with at this point, right? So our Kc, our equilibrium expression, is just going to be products over reactants. We can first look at the states of matter, and we can see that they're both gaseous, meaning we can include both of these species in our equilibrium expression. So now, that means the Kc for this will simply be NO, concentration of NO2 squared. Remember, we raise it to its coefficient, divided by the concentration of N2O4. N2O4. So this is going to be the expression. That's easy. We've done this before. Now we're at the step where we actually have to use our ice table. So in order to set up an ice table, what we do is here. Let's see if we can. No, I think we should have space for everything here. So let's say we have what our species is. So our species, and then what we'll have is our I, so our initial, our change, and an equilibrium. So we have this set up like this. What we do first is, again, write what our species are. So that would be N2O4. And NO2. So now all we have to do here is just fill out this table. So we start off with our initial concentrations, which is provided for us. The initial concentration for N2O4 is 0.100 molar. And for NO2, it is 0 molar. Now, what do we put in this change column? The change column, in order to figure out what goes here, we just have to reference our balanced chemical equation again. So basically what we see is in this reaction, we are converting N2O4 into NO2. And specifically, we can see that for every 1 unit or every 1 mole of N2O4 that we have, we produce 2 units or 2 moles of our NO2. And so we have to represent this symbolically in our change column. Because at equilibrium, what's happening is we're trying to find the concentrations of our 2 species, our reactants and our products. And the thing with these type of reversible reactions is, in order to produce any product, that is resulting from loss of our reactants. So what that means is, for every 1 unit of our N2O4, we can produce 2 units of our product, NO2. So we write this in this way. And then at equilibrium, what we would have is our initial concentration minus this x for our N2O4, and our initial concentration in this case is 0 for NO2, so we would end up with 2x. So this is what we're looking at for our ice table here. And so once we have these expressions that we can use that represent the concentrations at equilibrium, we can then plug these in to our K expression here. So that what that would be then is we would simply plug in 2x, right? 2x squared divided by 0.100 minus x. So this is what we're looking at here, and now what we actually have left out is the fact, here, let me just get rid of this, that we actually know what this is equal to. So we can say that this is equal to 0.005. That looks like a 6, 0.005. And so by solving for x in this sort of equation here, we would be able to figure out by what quantities our species are changing, or we can then figure out our concentrations at equilibrium. But something to keep in mind here is actually, you know what, well, at this point I think we've kind of understood the point of the ice table here, so we can clear it out of the way, just for the just so we can make some more space here. But what you'll notice, or rather what we'll see that we can use here, is an approximation. And what I mean by that is we see that this Kc is a very small value here. It's a lot less than 1. It's 0.005. And what does that tell us? Well, that tells us that the reaction actually hardly proceeds forward. And how do we know this? Well, what is our K value, or what is our K even showing us, right? Our K is really just our products divided by our reactants. So if we have a very small K value, what that means is that we have very little product and a lot of reactant. And remember, our products are forming from our reactants. So if we have these if we have a very small amount of product and a very high amount of reactant still remaining, what that means is that this reaction did not really proceed forward very much at all. And so because of that, what we can say then is that this X, right, the amount of our N2O4 that is converted is so small, it is so small that it's essentially negligible. What that means is we can say that the 0.100 minus X is basically, or just approximately, just 0.100. 100. And what that means now is that if we use this in this above expression, we can say that 2x squared divided by 0.100, right? Because 0.100 minus x is approximately just 0.100, because our x value here is so small, seeing as this reaction has not proceeded to a significant extent in the forward direction. And so now this is equal to our 0.005. And now what we're left with is a very simple algebra problem. So all we have to do then is solve for x. Excuse me, this is 2x squared. So rather what this would be is, or this is 2x, the whole thing squared. So this is 4x squared. So we're left with a very simple algebra problem where, again, here if we solve for x, we end up getting that our x value is 0.011 molar. And then now if we wanted to, so here, let's do this. Let's clear up some room again. So we figured out that our x is 0.011 molar. So now if we want to figure out our N2O4 concentration at equilibrium and our NO2 concentration at equilibrium, all we have to do is plug in this x value into the respective spots. So we know that N2O4 is just going to be 0.100 minus x, and in this case we found out x to be 0.011. So this gives us an approximate concentration at equilibrium to be 0.089 molar. And now for our NO2, that is going to be 2x. And again, x here is 0.011. So we then get an approximate value for our equilibrium concentration to be 0.022 molar. So this here is going to be our answer, right? Or at least that's what it seems as of now. But we are actually missing one step. And what that step is when we're actually using an approximation, as we did in this problem or in here in the solution, we need to actually compare what our x value is compared to the initial concentration. What that means is we have to compare this 0.011 to our 0.100 molar. And what the borderline here is, or what we have to see is, if this x value is less than or equal to 5% of our initial concentration, then it is small enough to be negligible and we can use this approximation. But if our x turns out to be greater than this 5%, greater than 5% of our initial concentration, well, that means that it is too large for us to assume it to be negligible for this denominator here. And what that means is we would actually have to solve this whole expression algebraically, and we cannot just use our approximation. And in this case, we can see that 0.011 is actually approximately 11% of 0.1. And what that means is it's above that acceptable 5%. So that means that we cannot actually use this approximation, and these answers would end up being inaccurate. So this is kind of a good teaching moment here, teaching or example, where we can see that we cannot actually use an approximation here. So now what that means is we have to kind of get rid of all of this and solve this using our quadratic formula, or just solve this properly rather. So let's do that then. Okay, so to do this, let's first maybe clear up some room here because we're probably going to need it. So we can see, oops, this is what we're trying to solve, right? 0.005 is equal to our 4x squared divided by 0.1 minus x. So we can begin by, multiplying both sides by this denominator here. It's going to give us 0.005 times 0.1 x, and this is equal to our 4x squared. Distributing this out, we get 0.0005 minus 0.005 x equals 4x squared. And we can set this up like a quadratic equation by effectively moving over the 4x squared to the same side. And what it gives us is 4x squared plus 0.005x minus 0.0005 is equal to 0. So now, again, we know that this is in the form of ax squared plus bx plus c. So we have our a is 4, b is 0.005, and c is negative 0.0005. So we can simply plug this into our quadratic formula, right? X is going to be equal to negative 0.005 plus or minus the square root. Remember, we square here, so that'll just give us 0. Or here, in order to get our b squared minus 4ac, I actually kind of already worked that out here, so I'm sure you guys should be familiar with the quadratic formula at this point. So just plug in the appropriate values, again, under our square root here in order to get our b squared minus 4ac. That's just 0.005 squared minus 4 times 4 times our c, which is negative 0.005. This is just going to give us 0.005 0, 0, 0, 2, 5, that's our b squared, minus 4ac is going to be giving us 0 plus 0 0.008. So if we simplify that, we end up getting 0 0.008025, 8025 divided by our 2a, right? For our quadratic formula, 2 times 4 is 8. So solving this is going to give us our values for x. It's going to give us our roots. But what you'll need to know again, in this case, is we're only dealing with our positive roots because there is no physical value or physical meaning to a negative value of x here. So solving for this gives us an answer of approximately 0.01057 molar. So that would be our x value here. So now that we've gotten this x here, let's clear up some space. We figured out this value of x. We can then finally get our equilibrium values, or our true equilibrium values, same way that we were doing so before. So our N2O4 is just going to be 0.1 minus this number. It's equal to approximately 0.089. My pen seems to be giving me some trouble again. 8943 molar. And then for our NO2, it's just 2 times this number, 2 times x, 0.01057, which is equal to 0.02115 molar. So then these here are going to be our true equilibrium concentrations. So the method with approximation that we use is something that you can use. In fact, you will use that for a lot of problems. I just wanted to give you an example here where you couldn't. Because again, like we talked about, once you do your approximation, you need to check whether the value of x is less than or equal to 5% of our initial concentration. And in this case, it wasn't, right? Because our x over 100, we look at our x value divided by our initial concentration, again, times 100%. Our x value, I erased it here, but that gives you an answer of approximately 10.6%, which is significantly greater than our allowed 5%. So what you need to do again is you need to check your approximation value to see if it ends up being less than or equal to 5%. If not, you're going to have to end up doing this entire tedious quadratic formula process. So that is how we do this problem. Hopefully it made some sense there. I know we kind of went one direction and then jumped towards the end there into another thing with all this quadratic formula nonsense, but that's the way that we do these problems. Ice tables really do simplify this whole process by organizing these quantities a lot more easily and a lot more clearly. So, definitely use those to your advantage here, and just make sure when you are doing so that when you can use your approximations, it saves you a lot of steps, so you don't have and a lot of time, so you don't have to go through this entire ordeal of using the quadratic formula. But always make sure to check your approximation at the end. So, that brings us to the end of this video. Hopefully, ice tables make some sense. You see how to set them up and how we can use them. Again, keep in mind those key rules. Try to notice when your k value is very small so you can neglect or you can assume that minus x value is negligible. Use the approximation. And then always make sure to check that x is less than or equal to 5% of your initial concentration. Alright, keeping that in mind, that brings us to the end of this video. Hopefully, again, it was useful. If it was, please show your support by liking and subscribing. Leave in the comments any questions you may have, what you'd like to see next, and I'll see you in the next video.